derivatives of trigonometric functions. So we've already talked about the derivative of sine and cosine. So we're going to talk about the derivatives of all the other things, which if you remember, I told you can get by doing the quotient rule for, like things like tangent, cotangent, and so on. You can use the quotient rule, and then you can simplify down, okay? So if you're stuck, you can always do that, but really, you should memorize these because you want to know how to do them quickly on the AP test, okay? So the first thing, derivative of sine, do you guys remember what it is? Yeah, cosine. You're a sixth of the way done with memorizing these. So cosine, negative sine, exactly. So when it says find the equation of the tangent line to y equals 2 sine of x plus cosine of x, we just take the derivative. So y prime is equal to 2 derivative of cosine, or derivative of sine is cosine, plus derivative of cosine is negative sine. And we want to find the equation of the tangent line at the point 0, 1. So we plug in 0 to find the slope. So cosine of 0 minus sine of 0. So cosine of 0 is going to be 1, and sine of 0 is 0. So we have 2 times 1, which is 2. So when we write the equation of the tangent line, we're through the point 0, 1. What's the nice thing about that point? It's a y-intercept, right? Right, 0, 1. It's a y-intercept. That's your b value, so you can just write it in the form y equals mx plus b, and you're done. All right, if you wrote it as y minus 1 equals 2 times the quantity of x minus 0, that's totally fine as well. You can leave it like that as well. Okay? So the next one, so it says use the quotient rule to find the derivative of each of the following. So if we have cotangent of x, we know that that is cosine over sine, because it's the reciprocal of tangent, which is sine over cosine. So we take the derivative by doing our low d high minus high d low all over the square of what's below. Do you guys all have that memorized now? Yeah. Some people don't do it. I had to do it. So, see, now I just messed it up. I'm talking as I'm. So low d high derivative of cosine is negative sine minus high d low derivative of sine is cosine all over the square of what's below. So we get negative sine squared minus cosine squared. What is that going to be? Yeah, negative 1, right? You guys see how you can pull out a negative from both of them and you'd get sine squared plus cosine squared? So we get negative 1 over sine squared. So how do you think we write it?
Did you get the sine squared x on the bottom?
All over the square of what's below. So it's the square of what's below. So how do you think we write the derivative? That's it. Negative cosecant squared x. So that is the derivative of cotangent. All right, the derivative of secant, same idea. So be active note takers, try it along with me. So secant we know is 1 over cosine. So this one will be easier because the derivative of the high is 0, so a lot of this is going to go away, right? So we're going to have low d high is 0 minus high d low derivative of cosine is negative sine all over the square of what's below. So we get positive sine over cosine squared. Okay, and you could leave it like that, but we have a simplified version where it's all like on one line basically. So what we're going to do is we're going to break it apart into sine over cosine and 1 over cosine. Okay, so I'm going to do 1 over cosine of x times sine over cosine of x. Do you guys see how that multiplies to be the same thing? If you multiply across the top, you have sine of x. If you multiply across the bottom, you get cosine squared. So we just kind of broke it apart into 2 separate fractions. Katie, did you get it? Okay. So what's 1 over cosine? Secant. So we get secant x. And sine over cosine? Tangent. So secant x, tangent x. So the derivative of secant x is secant x, tangent x. All right, so you should be memorizing these for sure. All right, cosecant. So it's 1 over sine. So we get low d high is 0 minus high d low is cosine all over the square of what's below. So we get negative cosine of x all over sine squared x.
Do always plug in like you plug in 0.
Because the derivative of 1 is 0. Does that make sense? So the derivative of the high part is 0, yeah. So when it's just a number, the derivative is 0. All right, so we break it apart. So I'm going to do the same kind of thing. So I'm going to have 1 over sine, and I'm going to do cosine over sine, but I don't want to forget that it's negative as well, so I'm going to put a negative all the way up front. So our answer is negative cosecant x cotangent x. So the derivative of cosecant is negative cosecant x cotangent x.
So, sorry, like on the top, like on the first one.
Yep.
You did sine x of 0 because we did like low.
So low derivative of high is 0.
How did you get the minus 1?
So minus high and then d low.
So not minus the derivative of high.
Right, minus
okay,
the high, yeah. All right, next page. Or next part. I don't know if you guys are on another page. All right, so you have all of the derivatives. So this is, like I said, pretty important because on the AP test, a lot of it is like, it's timed, right? All of it's timed, so you have to know how to quickly do these things. You shouldn't like be deriving these every single time. So we know the derivative of sine and cosine, I think. So the derivative of sine is cosine. The derivative of cosine is negative sine. So I think you guys are good there. All right, so the derivative of tangent we did the other day, it's secant squared x. And cotangent looks like it, but it's going to gain a negative and a co. So it's going to be negative cosecant squared x. So see how those two kind of go together? This one and this one go together. So the co-functions are similar. And the same with cosecant and secant. With cosecant, its derivative is negative cosecant x cotangent x. And then the secant is secant x tangent x. So as long as you know, if you know secant and tangent, then their co-versions gain a negative and a co for each thing, right? Do you guys see? So like this is related to this one because there's a negative out front and cosecant or secant changed to cosecant, tangent changed to cotangent. Do you guys see the pattern? Okay, so use that to kind of memorize these. So it says whenever I forget one of these derivatives, I just use the quotient. I never forget them. Like, I don't know. I don't forget these derivatives. I know these derivatives by now, right? I've been teaching for a very long time. But when I used to forget these, I would use the quotient rule and the derivatives of sine and cosine. All right, so the 30th derivative. Oh, my God. All we've done so far is the second derivative one time. Now we need the 30th derivative. Wow. Do you think there's probably a pattern?
Is it like doing I to the 48th?
It is very similar to doing like I to the 48th. Exactly. There's a pattern. Okay. So do you think it's 4 every 4? Every 2? I don't know.
I think it's 3.
So if our original is sine, so y equals sine of x, y prime is going to be the derivative of sine is cosine. Y double prime is going to be negative sine, so it's not every 2. Y triple prime is going to be negative cosine, exactly. The 4th derivative, do you guys think we do this like for the 30th? Eventually we have to stop doing that, right? So once we get to the 4th, that's when we do a parenthesis in 4, like that. So it looks like y of 4, but it's actually raised up. So that is read the 4th derivative of y is, it's back to sine, okay. So what do we think? So the 5th derivative is going to go back to cosine, and so on. So I'm going to write this, I'm going to line them up. So I'm going to say, okay, well the 4th was back to sine, so the 5th was back to cosine, etc. So what's this next one? To be back at sine? This would be 6, 7, 8, right? So what's the pattern? Every 4, yeah. So we wanted to basically take 30 and divide it by 4. So when I take 30 divided by 4, that means I'm going to have 28 goes evenly, right? And then I'm going to have the 29th, and then I'm going to have the 30th derivative. So our 30th derivative should be the same as the second derivative, which is negative sine of x. So basically whatever its remainder is, that's the derivative you have. So if it goes evenly, no remainder, it's the same as y. The 0th derivative, we don't really say that. Yeah, so it ends up being negative sine. Do you see the pattern? So that happens for both sine and cosine. It's every 4. All right, number 2. So it says differentiate f of x equals cosine of x over 2 plus sine of x. For what values of x does the graph of f have a horizontal tangent? Okay, so we're going to do low. I was too speedy. So we're going to do low d high. So the derivative of cosine is negative sine minus high cosine. D low, so what's the derivative of 2 plus sine of x? Just, not sine, cosine, right? Did you say cosine? Okay. Yeah, cosine of x, yeah. All over the square of what's below, so 2 plus sine of x.
You found
squared.
the derivative of the 2 sine of it?
So the derivative of 2 is 0, and then derivative of sine is cosine, yeah. So we continue to simplify. Remember, when we're lazy, we can do like the little, like quote signs or whatever on the bottom. I don't know why I did squared as well. You can just do quote signs if you want. And say, okay, same derivative, or same denominator. All right, so when I multiply it in, I get negative 2 sine of x. So I'm multiplying this in here and here. Minus sine squared x minus cosine squared x. Notice how that's happening a lot. So we have negative sine squared minus cosine squared. So that's negative 1. So we're going to have negative 2 sine of x minus 1 because of that minus sine of x minus cosine of x. And then we have that 2 plus sine of x on the bottom squared. So we want to find when it has a horizontal tangent. So we've done these before. Horizontal tangent means what? Slope equals 0, so f prime equals 0. So we're going to set our f prime equal to 0. And we have a fraction. So the fraction is only equal to 0 if the denominator is, or not denominator, if the numerator is equal to 0, right? This denominator will actually never be equal to 0. Do you guys see that?
Yeah.
So there's no location of a vertical tangent or a place where the slope is undefined, right? Because you can never have sine of x equaling negative 2. You're not going to get a 0 in the denominator. But we could have a horizontal, so we're going to set our numerator equal to 0. So we're going to say negative 2 sine of x minus 1 equals 0. So when I add the 1 over and divide by negative 2, I get sine of x equals negative 1/2. So sine is equal to negative 1/2 in 2 locations on the interval 0 to 2 pi. I didn't say on the interval of 0 to 2 pi, did I? So we're going to have 5 pi over 6 and, or no, 7 pi over 6 and what else? 7 pi over 6 and 11 pi over 6. So the easiest way to write your final answers would be 7 pi over 6 plus 2 pi k and 11 pi over 6 plus 2 pi k. So every rotation of the circle, you're going to have another one. Yeah.
Why do we set negative sine squared x and negative cos squared x equals 0?
It's, sorry, that's arrows pointing to the horizontal tangent thing. It's equal to negative 1. So negative sine squared minus cosine squared is negative 1. Do you remember sine squared plus cosine squared is 1? Yeah, that's what we're doing. All right, makes sense? So it's the same concepts that we've done before. We're still setting the numerator equal to 0 when we say horizontal tangent.
So, like, every time it says on the horizontal tangent, you just...
Yeah, you're finding when the slope is equal to 0, yeah. So if you add a fraction, then it's when your numerator is equal to 0. All right, so number 3. So find the equation of the tangent line to the curve at the point pi over 3, 2 pi over 3. So, all right, so if I have f prime, right, I need to find the slope. So when I have x times secant of x, okay, do you guys all see that that needs the product rule? Because we know how to take the derivative of x individually, right? The derivative of x is 1. And we know how to take the derivative of secant individually, secant x tangent x. But we can't just like take the derivative of each individual thing. Okay, that's just like if you had like x times x squared. The derivative is not 1 times 2x, right? We talked about that. Do you guys see what I'm saying? So we have to do the product rule here. So we're going to break it apart into the 2 functions. So we have x and we have secant x. And we're going to use that product rule. So I have first is x, derivative of the second. So the derivative of secant of x is secant x tangent x. So secant x tangent x. Plus the derivative of the first is 1. Second one normal is secant x. Okay, and I want to find my slope at the point pi over 3 comma 2 pi over 3. So I'm going to plug in pi over 3 to find my m, my slope. So it's going to get a little messy. So I have pi over 3, and then I have secant of pi over 3 times tangent of pi over 3 plus secant of pi over 3. Yikes. It's not pretty. If it was the exact value, it's not going to be fun. Finding a decimal version of this is when, with the AP test, you're like, okay, I'm just going to round to 3 decimals. Because it's really gross, because it's going to involve a root and a pi. Right? So if you were rounding to 3 decimals, you would just put this all in. So let me do this, and then I'll find the exact value too.
On the test we do like in here, are we going to be finding the exact value?
You probably won't have one this hard. But you might have one that has like sine of pi over 3 or something. Right? How do you put in cosine on your calculator? Do you guys, or not cosine, dang it, I gave you that. How do you put in pi, secant of pi over 3? 1 over cosine of pi over 3, yeah. I do that all the time. So I have pi over 3 times 1 over cosine of pi over 3 times tangent of pi over 3, and then plus 1 over cosine of pi over 3. So you guys all do that. I got 5.62, I'm going to round up, so it was 627,598, blah, 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 so I'm going to say 628. So that would be the easiest way to find it. If you have your calculator, just go ahead and do it, because we know that the AP test accepts 3 decimals, right? That's why I engraved it in you in pre-calc, 3 decimals all the time, right?
Is the AP test all calculator?
No. 2/3 of the test is non-calculator. Don't you hate that? So this would be a perfectly acceptable answer. They would accept this if it was on the calculator portion. But what if it was on the non-calculator? It would be all right. You could handle it. So we would have pi over 3. What is the secant of pi over 3? Well, first of all, what's cosine of pi over 3? You guys all know that. 1 over 2, right? So what's secant? 2 over 1, right? It's the reciprocal. So we have 2 over 1. But tangent of pi over 3 isn't as nice. So tangent of pi over 3, if we're up at pi over 3, it's 1/2 comma root 3 over 2. So the tangent is going to be what number? Square root of 3, right? Because you're going to do square root of 3 over 2 divided by 1/2. So square root of 3 over 2 divided by 1/2 is square root of 3. And then we have plus secant of pi over 3 is 2 over 1, or 2. So if we were writing this in a simplified form, it'd be 2 pi root 3 all over 3. Good luck today. Plus 2. That is our slope. That's why I thought it would be easier to write the decimal version, because it's kind of weird to put that right here, right? So you would put an n in parentheses. So it would look like y minus 2 pi over 3 equals 2 pi root 3 plus 2 over 3 plus 2 in parentheses, that whole slope, times x minus pi over 3. Oh, gross. Don't you hate it when it says find the exact value? That would be the exact value for the slope. All right. Anything else? Yeah, a couple more. Got that down?
I think my answer on the calculator is kind of like around to 1.01.
Okay.
1.01.
It's probably a parenthesis thing. Did you guys get the 5.628 number? You did? Okay. Yeah, I'll look for your parentheses. All right, and the last one, so it says an elastic band is hung on a hook, and a mass is hung on the lower end of the hook. Okay, so we actually do use trig values a lot in real life. We use it for things like this, like a spring, but you also use it for things like currents or temperature during the day. It's kind of a sine function, so it's cool in the morning, gets hot, and then it cools off again at night. So yeah, we would use like sine function for a lot of things. So it says when the mass is pulled downward and then released, it vibrates vertically. The equation of motion is -2 sine of t plus 5, where t is greater than or equal to 0. S is in centimeters, so it's some kind of distance, right, or displacement, and t is in seconds. So use your calculator to help answer the following questions. So find the velocity and acceleration after t seconds. So we're not going to do anything on our calculator here, we're just going to go ahead and find the derivative of our position function to get velocity. So the derivative of negative 2 sine of t plus 5 is going to be negative 2 times cosine of t.
What about the derivative of like -2?
Well, the negative 2 just kind of got pulled out to the front. So if you had done product rule, it'd be negative 2 times cosine of t plus the derivative of negative 2 is 0 times sine of t.
Okay.
So it'd all go away, right? All right, and then the acceleration is going to be the second derivative of position. So it's the derivative of velocity. So it's going to be negative 2 times negative sine of t, which is just 2 sine of t. Okay, so we're going to use our calculator. So it says, when is the speed the greatest? So speed, as I've told you before, speed is the absolute value of velocity. Okay, so that's important. So we can graph the velocity function and then just think, oh yeah, I'm going to use the positive versions of those numbers. Or you can actually graph the absolute value of your velocity, right? So you could graph the absolute value of negative 2 cosine of t. So let's go ahead and do that. So go ahead and put that into your calculator. Do you guys remember how to get an absolute value? Yeah, so you do math, you go over to number. It's the first choice, abs. So absolute value. And then we do negative 2 cosine of t. So t we're just going to put in as x. And just make sure that you're in radian mode. You should be already. And we're going to graph. And I'm guessing that it's going to be kind of tiny. We'll see. That's not too bad. All right, so it says, when is the speed the greatest? So we just graphed the speed function. So we're finding when it's at its highest point, right? So it looks like at 0, something else, something else. So let's find it. So if we find our, do second trace and we find the maximum, we would do arrow over, left bound, get on the left of what you want, right bound, get on the right of what you want. And then guess, I usually put it where I think it is, or you can just hit enter again, it's fine. And it says the maximum is 3.14159, blah, 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 comma 2. Okay, this calculator rounded a little bit. Those of you that have memorized pi, you know that this is not pi. 3.1415926 is how it goes. So it's rounding, it's messed up. But do we think it's at pi? I don't know, let's think about it. Right, if you were setting the velocity and trying to find where it's the greatest, another thing that you could do if you didn't have your calculators, you could take the derivative and find where your derivative, where you have a horizontal tangent, right? So we could find the derivative, which would be acceleration, and then set it equal to 0. So that's another way of doing it, but yes, it would be at pi. So this would be at t equals pi, and then it continues. So there's other places, right? So really, I mean, a spring won't do this, like as you pull the hook down, or elastic band, I guess. As you pull the hook down, it's not going to continue to go up, down, up, down, up, down indefinitely. There's a lot of other things at play. This is why you take physics, right? You learn air resistance. You learn about the resistance of the band eventually. So it's not going to continue going forever. But if it did, where's this next one? What did you say? Drag? Yeah. So let's find it. So what do we think it's at? Yeah, Ariana, do you have a question? Okay, so too far. Are you in radian mode? Did you check that? Okay, at the very top, do you have plot 1 highlighted? Does it say dimension or something? What does it say? Okay, so hit Y1. So here, I'll show you up here. So when you hit Y1, plot 1 should not be highlighted. So go up to plot 1 and de-highlight it if it is. Was that highlighted? And then another thing you guys can do if you're still getting an error, do second zoom and go to your, oops, second zoom. Or I don't know why I'm doing second. Just zoom and then go to zoom 6. And that will put it on the standard window, because sometimes your window is like incorrect. Like maybe you say go from x equals -2 back to -5. That doesn't make any sense. You'd have to go from -2 to 5 or something, like a bigger number. Okay, so then that's going to be probably a negative. You probably use the minus. So use the negative down here, yeah. So many errors your calculator can give you. All right, does everybody have it? So what's our answer then? So t equals, you could say pi plus pi k, or you could just say 0 plus pi k, or you could just say pi k, right? Where k is an integer. All right, next problem. Oh, that's it. We're done. That wasn't hard. I feel like I used to ask other questions there. It used to be harder. Yeah. Uh-huh.
Where are we looking on the graph to get t equals pi?
You were looking at the x value. So when I did second trace and I found the maximum, I'm tracing along here, and when it says left bound, right bound, I want to get on the left of the maximum, and then I want to get on the right of the maximum, and then I guess where I think it is. And then down here at the bottom, it says x equals 3.1415. Do you guys see that? So it's the x value. And then the highest speed that it has is 2. So if I was asking for, like, what is the highest speed, it would be 2 centimeters per second. Okay.